Hey, science nerds, and welcome to the second half of our discussion on topic 1.4 electric circuits. Last day I discussed the relationship between voltage, current, and resistance, otherwise known as Ohm's law, in which voltage is equal to current times resistance. Today we're going to apply that law and we're going to see how it plays out when we use it in the two main types of electrical circuits, one being the series circuit and the other one being the parallel circuit, and the differences in how we calculate either voltage or resistance in either of those circuits. And we'll get to that before the end of today's discussion. To start off with, and I just showed this last day when I drew a very generalized uh, view of a circuit. I used what was called a schematic or a schematic diagram, which uses specific symbols which are universally accepted by electricians. And it just allows us to draw these circuits very easily and efficiently. And using these symbols, it just makes it very easy for anyone in any country to understand what an electrician is drawing when using these specific symbols. These symbols, by the way, are if you have to draw a circuit, and you might have to draw, you know, some simple circuits as part of your questions or possibly on an exam or a quiz in the course. The symbols that are used for a circuit are outlined on page 374 of your textbook. Now keep this in mind, you'll never be expected to draw a circuit on a diploma exam, but you would have to be able to recognize one and being able to recognize some of these standard symbols. These are not shown in your data booklet, so you are sort of expected to memorize some of the major symbols of a circuit. Like for example, on my diagram here, if I've got this tall and the short line side by side there, that would represent a cell, a power cell of some sort. The circles with the X's running through them would be some kind of a load that is being powered on the circuit, and the actual square line would be the actual conductive wire that's in the circuit. So I'll be showing you a few symbols here today and ones that you should be familiar with, and I'll walk you through them as we go through today's lesson. But be aware that all the symbols that would come at you in this course are going to be shown in that table on page 374 of your textbook. All right, so what are the two main types of circuits? Well, I've mentioned them, and we're going to use schematic diagrams for. There are series versus parallel circuits, and you might be familiar with the concept of a series versus a parallel circuit, but let me just kind of explain the difference between the two. A series circuit is basically a single pathway for all the electrons to flow through. So basically, there's only going to be one current running through the entire circuit. That current is never really going to change because there is only one current to run through. This means that the current passes through all the load resistors in they're all controlled together. So anything you put in a series circuit, they're all going to be kind of they're all, whatever you do for one, you're going to do for all of them kind of thing. So for example, if I put a switch in here on this circuit, and we talked about switches last day, if I open up this circuit with that switch and I open the switch, that's going to shut off all my load resistors at once. If I have, let's say, two light bulbs, or in this case, I have two light bulbs or three light bulbs on a series circuit, if I shut off one, I shut them all off at the same time. Contrary to that would be a parallel circuit. A parallel circuit has multiple pathways for the electrons to flow through, and I can control separate devices on separate parts of the circuit. So for example, if I put a switch here, that would only affect that load resistor that is on that part of the circuit. If I put a switch here, for example, that would only affect that load resistor there. I could, in theory, put a switch here that would, in fact, control both of them. But the beauty of a parallel circuit is that you can basically you can control each load resistor independently. And the other advantage of a parallel versus a series circuit is you're going to have less in the way of resistance, which I'll get to later today. But generally speaking, when you have a parallel circuit configuration, there is going to be less resistance in total on that circuit, as opposed to if you have all of your load resistors in a series, that increases the amount of resistance that's going to be found in that particular circuit. And how do these circuits differ, as you can see there on the slide? Well, again, I've shown you them up here on the board. There's some stuff here in the notes for you to take a look at as well. But here is your classic example. Can I tell that this is actually a series circuit? Absolutely, I can. It's one single square with two load resistors together on one line. That is clearly going to be a series circuit. This one here is clearly going to be a parallel circuit because both of my load resistors are going to be on separate pathways in a circuit. However, I can have combinations of both. For example, I could draw a circuit that is both parallel and series. So for example, if I drew this configuration here, let me just draw there's my cell. I would see a line like that, and right away you're thinking, well, this is going to be a parallel circuit. Perhaps. However, here's the trick. Here's the trick. I'm going to do this. So what I'm going to do here is I've drawn now 3 load resistors on my circuit. This load resistor is parallel to these load resistors. However, these load resistors, because they're on the same line, are going to be in a series configuration to one another. So this is load resistor 1, load resistor 2, and load resistor 3. Load resistor 3 right now is parallel to 1 and 2, but 1 is in series to 2. So you got to keep that in mind, that just because you see what looks like a parallel circuit doesn't always mean that all the resistors, the load resistors in that configuration, are going to be automatically in a parallel configuration. You do have to pay attention. If there are more than one load resistor on one branch of that parallel circuit, then those load resistors that are on that one path together are going to be in a series configuration to one another, whereas they would be parallel to all the other load resistors on the circuit. So please keep that in mind. You might see something like that in a diagram at some point. Okay, now how do we measure all of our 3 measurements, voltage, resistance, and current, when we're looking at a circuit? Well, there are 3 types of meters that we can use. Generally speaking, an electrician is going to use what's called a multimeter. A multimeter would have the capability to measure all 3 of these, but technically you have separate meters for each measurement. So for example, if I'm going to measure current, I'm going to use what's called an ammeter. And an ammeter on a circuit would be drawn as a circle with an A in the middle of it. So anytime you see in a circuit a circle with an A in the middle, you realize that that's an ammeter. And ammeters would be configured on the circuit. They would actually be placed directly on the circuit. So if I had an ammeter, say on this circuit right there, I would put the ammeter directly on the spot of where the current is running through. In this case, the current's running through that part of the conductive wire. So I would make the ammeter, I'd put it right on the actual circuit. If I want to measure voltage or a voltage drop over a load resistor or over a load, I would not place the voltmeter on one side of the object or of the resistor. I would have to actually have measurements on both sides of the resistor to indicate what the voltage was before it entered the resistor and what the voltage was after I exited the resistor. So in that case, if I was drawing a voltmeter would actually have a side path like so, and that's how you would see a voltmeter placed onto a circuit. It would be on either side of a load resistor to indicate how much voltage was actually being used or being lost over that resistor that's being converted to another form of energy. How much of that electricity is now being converted into, say, heat or light, if it's a light bulb or something like that. But I can't measure voltage like just on the line, because if there's nothing to compare voltage to, I can't tell how much of a volt drop there's been. I would do the same thing if I was measuring a battery. I'm measuring the voltage of a battery. Again, I'd have to put one of my voltmeter terminals on the positive cathode or electrode of the battery, and one of the measurements would have to be done on the negative or the anode side of the battery or the cell. And then I could actually measure the voltage difference. If it was, let's say, a AA battery, if it was a full battery, I should see 1.5 volts because that's the standard voltage of a AA battery. If it's empty, I might see down to like 0.4, 0.5 volts. I can see that battery has almost been depleted at that point. And the last measuring tool that we can use is called an ohm meter, and it's going to measure resistance, and it's going to be configured the same way a voltmeter would be. It has to be before and after a load resistor of some sort. So, and I'm going to have that little ohms symbol there. It didn't draw very well. That did not draw well at all. All I got is a big blue circle there now. Let's try that again. My ohm meter is going to use the circle with the omega symbol inside of it, which is our symbol for ohms, as I discussed last day. But again, an ohm meter has to be placed before and after a resistor to indicate how much resistance is actually on that resistor. I can't just put an ohm meter on a circuit directly like I would an ammeter, otherwise I would get no reading. I would get a reading of, there would be no resistance at all, so I get a measurement of zero because there's no relative change in the current. I'd have to see that there's a change in the current in order to determine if there was if there's resistance on that part of the line. So just be aware of that ammeters are going to be placed directly on the circuit, and voltmeters and ohm meters are going to be placed off to the side of the circuit. That's the way they have to be configured in order to get their readings properly. And the diagram I've given you here is sort of explaining that as well. There is no diagram of an ohm meter there, but just be aware the configuration of a voltmeter would be pretty much the exact same configuration of how you would put an ohm meter on that circuit as well. All right, so what does this all mean? Well, here's an example. Here's a circuit we've got right now. I've got 3 light bulbs in a series configuration. I've got a battery over here. I've got voltmeter 1, voltmeter 2, voltmeter 3, voltmeter 4, and I've got an ammeter on the line. Let's answer a couple of questions about this configuration. I've got positions Z and X that I'm going to be referring to in this diagram. Would an ammeter give the same reading if it was positioned at Z or if it was positioned at X? Would it give the same reading if I put the ammeter here as opposed to if I put the ammeter there? Think about that for a second. Maybe think about your answer, and also think about the why. You know, if there is a change, why would that be happening? Give you a couple seconds to think about that. Pause me if you need to. All right, here's the answer. The answer is no. If I put the ammeter on Z, that is actually the correct positioning, but that doesn't answer my question. If I put the ammeter over here off to the side, if I get a reading here, the problem is I've created a parallel configuration around a load resistor. So if this is a load resistor, it's resisting the current that's going through it. So in theory, what's going to happen is potentially more current is going to flow in this direction as opposed to that direction. So what's going to happen is you're going to see not all the current is flowing on that line. Some of it will flow through the load resistor, and that's actually going to potentially, well, it will change your result of the current because you've essentially got a split in the river where electrons can flow in 2 different directions. So you're not measuring the full current. It'd be like if I had a river and the river splits off into 2, and I want to measure the current on one of those side streams. The main current of the river is going to be more than either one of the side streams that are going off in either direction. And that's what's happening here. I've got a split in my circuit. So that isn't going to give me the same reading. So that's why we would want to place it on the Z position, because that would be the accurate reading for the actual total amount of current that's running on the circuit. X would not be a good spot to put your ammeter. All right. Next one. Would a voltmeter work if I positioned a voltmeter on Z? Why or why not? Think about why or why not. Think about it. Pause me if you need to. And here it comes. Z would give me no reading at all. If I put a voltmeter at Z, I would get a reading of 0. Why? Because a voltmeter is based on a voltage drop. I have to see some kind of a voltage drop. I'm having nothing to compare to here. I just have I need to see what's happening over two parts of a circuit. For example, if I took my voltmeter and I had my two little positions for my voltmeter and I measured here and here, in theory, there's no volt drop there. Because not in theory, because there's nothing to actually drop the voltage on that section of the circuit. There's no resistor, there's no load resistor in play there. I have to measure, anytime I have a voltage drop, I have to place my voltmeter across on either side of a resistor, on either side of a load resistor. There has to be some kind of an object there in the circuit that's going to cause a voltage drop. So the position of voltmeter 4, 3, 2, and 1 are all in the correct positions, but this is why you can't place a voltmeter directly on the circuit. It won't work, and nor will it if it was an ohm meter either. An ohm meter would have to be placed in the same configuration as voltmeter 1, 2, 3, or 4. So just hopefully that makes it clear as to how voltmeters need to be placed on a circuit as opposed to ammeters, and as well as your all your meters that do all your measuring, voltmeters, ammeters, and ohm meters. Quick video review right here. Watch this sucker really quickly before I start doing calculations on how to do parallel, how do you calculate resistance and voltage on a series versus a parallel circuit. Give that video a watch before I get started right now. All right. So how do we actually do the math? How do we do actual calculations now? Now that we know what a series is versus a parallel circuit, now that we understand where voltmeters have to go, where ammeters have to go, where ohm meters have to go, how can I do calculations to calculate, my overall voltage, my overall resistance, my overall current on a circuit? Let's take a look at a couple of formulas here that you're going to need to be aware of. By the way, all of these formulas are going to be in top of page 3, right there. Electrical formulas, right there and right there. Those are some of the formulas right there you're going to need to be aware of for this section of the unit. Let's take a look. We're going to start off with series circuits first. Series circuits, here's a couple of things you need to be aware of. The current is exactly the same no matter where you go on a series circuit. The current never changes because there's only one path for the current to actually take. So if you're measuring the current here versus the current over there, as long as you're actually on the main line, you are going to get the same amount of current no matter where you are on the circuit. That will not change. So once you've calculated the current anywhere on a series circuit, that number will not change anywhere on the circuit. The total voltage in a series circuit is a sum of all the voltages that are on the circuit. So for example, if I had, let's say I had 3 AA batteries that were placed in a series configuration on a circuit. Each of those AA batteries has a voltage of 1.5. My total voltage at that point would be 4.5. 1.5 plus 1.5 plus 1.5. The formula for total voltage on a series circuit is voltage 1 plus voltage 2 plus voltage 3. Depends on how many batteries or cells are on that circuit. That's going to determine the total voltage. So all you have to do is find all the voltages of all the cells and batteries on a series circuit, add them up. That gives you the total voltage on the circuit, okay? The voltage will drop after each resistor that it encounters. So in this case, I've got 3 load resistors that are there, and I'll be doing the math on these in a couple of seconds, but you're going to have a voltage drop after the first one, a voltage drop after the second one, and a voltage drop after the third one. But here's the beauty of it. After the 3 voltage drops, the total voltage drop after these 3 load resistors, if you add up all 3 of those voltage drops, those 3 voltage drops will add up to the total voltages actually on the circuit. So if I had that total voltage, as I just mentioned, 3 AA batteries, all being 4.5, total of 4.5 volts on the circuit. If that was my total voltage, then my 3 voltage drops here, when I do my math for them, and I'm going to prove this to you in a couple of seconds, so don't worry, I'm not just doing smoke and mirrors here. There is going to be a correlation there. When I take all my voltage drops over my first, second, and third load resistors there, if I add all those 3 voltage drops up, it will add up to 4.5 if that's the voltage that's been determined as my total voltage. And I will prove that to you in just a couple of seconds. How do I determine the total resistance? My total resistance is going to be the total resistance I'm just going to add my resistances up. So in this case, I didn't really show you what the voltage was up here. I'll get to that in a couple seconds. But here I've got a I got a resistance of 3, a resistance of 1 ohm, and I got a resistance of 0.5 ohms. Just so happens it's the exact same number I gave. I gave a hypothetical voltage number. In this case, that's the actual numbers that were given to me on the circuit. But in this case, if I go 3 plus 1 plus 0.5, I am going to have a total resistance in this case of 4.5. So in this case, my total resistance on that circuit is going to be 4.5 ohms. All I have to do is add up my three load resistors or my 3 resistors to calculate the total number or the total amount of resistance. So these are your 2 formulas that you're going to use when you're calculating either the voltage and the resistance on a series circuit. And once you know the voltages and the resistance, then you can use Ohm's law, that V equals I times R, to calculate the current that's running through. And because the current never changes, once you know your current, you're kind of set. So I'll give you an example of that. In fact, we'll do it right now. This slide here, before you take a look at it, if you just slipped over to that slide, maybe cover it up. Don't look. All the answers are there. I'm going to walk you through this slide, all the answers on this slide one at a time, just to give you an idea of how to do the calculations based on what I just said. Here we go. The series circuit right there and on your slide has 2 cells that have 4.5 volts each. Okay, so I got 4.5 volts. Okay, perfect. I've got, so right now I need to do some calculations. Apparently I kicked Siri into action. I know the word I'm not supposed to use. It's Theory. When I say that word, she thinks I'm saying Siri. So I'll try to avoid saying that word because that always seems to set her off. Okay, so I've got a series circuit that has 2 4.5 volt batteries each. The resistance of each light bulb is shown. I showed you it's 3, 1 ohm, and 0.5 ohms. Sketch this into your notes and answer the following questions. Here's the first question. What's the total voltage of the circuit? Easy. I got 2 cells of 4.5 volts each. I'm going to use my formula for a series circuit. It's going to be voltage 1 plus voltage 2. So my total voltage in this case is going to be very easy. It's going to be 9.0 volts. Piece of cake. That one's easy. All right. What would the measurement be by voltmeter 4? Okay. What would the measurement be? Well, this is the battery. These are my 2 4.5 volt batteries. If I were to measure the strength of the battery, what would I get as a measurement there? That would be the measurement. That would be the measurement of 9.0 volts. That would be the measurement right there, because I'm measuring the total strength of my series of cells or batteries. That's going to be my reading it on voltage on my voltmeter 4. Will give me that value of 9.0 volts. What's the total resistance in the circuit? I already calculated this earlier. I showed it to you a couple of minutes ago. But again, I'm going to use this formula here. RT equals R1 plus R2, in this case, plus R3. I've got 3 plus 1 plus 0.5. So my total resistance is going to be 4.5 ohms. 4.5 ohms, easy peasy, nice and easy. That's easy enough. What's the current measured by the ammeter at position X? So if I'm at position X, which is right here, what is going to be my current that's measured? Now, I did mention something about currents in series circuits. Currents don't change. They stay the same all the way through the series circuit, regardless of what resistors are there or whatever. You're getting voltage drops, not a current drop in a series resistor or in a series circuit, pardon me. So in this case, I've got everything I need. I've got my voltage. I know that voltage is equal to I times R, right? Ohm's law. So I'm going to say voltage is 9.0 volts equals I times 4.5 ohms. So that means that I is going to be 2 amps. 2 amps is going to be my measurement at that point on the circuit. And quite frankly, that would be my measurement anywhere on the circuit because again, your voltage doesn't change in a series circuit. Your current does not change in a series circuit. Your voltage will change. Your current will change, but not your volt. Sorry, your current will not change. See, this is what she's doing to me. Your current will not change. Your voltage will drop as you go across resistors in a series circuit. That's another word she doesn't like either, as opposed to SIRI. She doesn't like that word apparently either. All right, let's do another one. Would it be the same at position X? I think there was supposed to be two questions there. There were supposed to be two things on there. There must be an error there. Would it be, let's say if I had, let's say position, let's say I had Z over here. It's just asking me if the current would be the same everywhere else. Yeah, it would be. It would be the same because we know the current's the same all the way through a series circuit. Now here comes the question. Now that I've got my current, and I know my current doesn't change, I know what my current is. Now I can calculate all of my voltage drops over voltmeter 1, voltmeter 2, voltmeter 3. Because I've got my current now, which is 2 amps, and I also have my resistance over each of those voltage drops. So I've got my I is equal to 2 amps. Now I'm going to use each of my load resistors' resistance to calculate the voltage drops over each of those load resistors. So in this case, I'm going to use my voltage equals I times R. So for my voltmeter 1 reading, I'm going to see 3 ohms. So I'm going to have 2 amps times 3 ohms, which is going to give me a volt drop over voltmeter 1 of 6 volts. Okay. The current, which I've already determined, based on, and then times that by the resistance of the load resistor of that device. Now I can do that for all 3 of my resistors. So I got 6 volts. I'm just going to put 6 volts down first because that's my first one. That's going to be voltmeter 1. That's going to be my reading of voltmeter 1 is going to be 6 volts. I'm going to be down 6 volts after voltage meter number 1. My second one is going to be 1 ohm. So that's going to give me, over the second one, I'm going to have a drop of 2 volts. So if I have 2 volts there, let me just draw my second arrow there because that's my second volt drop, right? 1 ohm times 2 amps is going to give me 2 volts. And then my last one is going to be 2 amps times 0.1 ohms is going to give me, pardon me, it's going to give me 1 volt. 2 times 0.5 is going to give me 1. So let me add that in there. That's going to be that one. Well, look at these numbers. I've got 6 plus 2 plus 1. I told you this earlier. The total amount of voltage drops over all of my resistors in a series circuit is going to equal the total voltage of the cells. And guess what my total voltage was to begin with? 9. 6 plus 2 plus 1 equals 9. It works because that's how a series circuit works. There's all the math for that underneath here that I just gave you, and the beauty of the fact that when we're done, all of them equal the total voltage. By the way, that is known as Kirchhoff's law. Kirchhoff's law, a very famous law in electrical physics, and a very important one because it is a universal truth, universal constant. So keep that in mind. So that's how you do all your calculations on a series circuit. That's actually pretty straightforward stuff because all it is just you're adding up numbers, and then once you've got your current, you can figure out your voltage drops off of each of your resistors that are in the particular circuit. So you kind of, the way I did it is a great way to kind of approach those questions. All right, where it gets a little bit crazier, a little tougher, is parallel circuits. Parallel circuits are not quite as straightforward. So let me explain a couple of differences between parallel versus series circuits. First of all, current does change. So we talked about how in series circuits the current does not change anywhere. It's always the same no matter where you go. Because you've got parallel lines and different paths for the electrons to flow through now, the current will change at various points inside of a parallel circuit. More electrons will go through pathways that have less resistance. So very much like a river, if I've got a path, like a deeper channel this way, more water might flow this way, and less water is going to flow through this section that's got more rocks in it or whatever. You're going to see more electrons flow through this path if there's less resistance than this path over here where there is more resistance. So because of that, current is going to change depending on which path of the parallel circuit you're in. Different than in a series circuit. Voltage of each of the parallel paths is equal and can be summarized by the equation. So now voltage is going to not, so that's the difference. In a series circuit, your voltage changes. In a series circuit, I love it when you have words like that that set it off every time. In a series circuit, the voltage drops, changes, the current does not. In a parallel circuit, it's the opposite. The voltage stays the same, the current will change depending on which path you're in. So that's a major distinction that you want to keep in mind that's going to separate series versus parallel circuits. How do you calculate it? Well then, because it's equal everywhere, the total voltage is going to equal voltage 1 plus voltage 2 plus voltage 3. So no matter where you are, once you know your total voltage, your voltage is going to stay the same no matter where you are inside of that parallel circuit. The resistance, though, is a little trickier to run by now. It is going to be 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So you're flipping it's sort of this equation up here, except it's now 1 over. And it's because of that, and you'll see in a few minutes here, this is why the resistance is much lower. Total resistance is much lower in a parallel configuration than it is in a series configuration in a circuit. And I'll get to an example of that here in a couple of seconds. In fact, I'm going to get to that example right now. If you see this page here, cover it up. See if you can actually work through it. I'm going to walk you through this question like I did with the series circuit. See how much of it you can do. All right, here's what we've got. We've got a parallel circuit. We've got the same, we have 3 resistors again, just like we did in our series circuit example, but now the resistors are in parallel configuration rather than a series configuration. So R1 is going to be 3 ohms, R2 is going to be 1 ohm, R3 is going to be 0.5 ohms. By the way, the squiggly lines are a way to represent with a schematic diagram a resistor. I gave you on the last slide, it was a load resistor, which was like a light bulb, or it could be some device that's going to convert electrical energy. In this case, we just have a device in the circuit called a resistor that's just impeding the flow of electrons, not necessarily converting to anything. It's just resisting the flow of electrons because we have to put a resistor inside the circuit for some reason. But that's what those squiggly lines are. They're resistors. Same battery configuration. I got 4.5 plus 4.5 volts. So that gives me my total voltage. I'll be able to figure out all of that. And then I've got several designations here. I've got position X, Y, W, V, and Z. And I'll be answering some questions about that here right away. Okay, here's the first question. What's the total voltage of circuit Z? Okay, and that's circuit Z here, which would be, so at the Z position, what would my voltage be? Figure it out. Pause me if you need to. I'm going to give you the answer right now. Same as before. It's going to be total voltage. In this case, because they're in, now remember, this is one of these examples where the cells are now in a series configuration, even though it's a parallel circuit, these two cells are in a series configuration. So I'm going to basically use my series equation rather than my parallel equation. In this case, I've got 4.5 plus 4.5. That means that I've got a total of 9 volts. So I've got 9 volts going on. That's my total voltage is 9.0, just like in the last equation. Be aware, if the cells were arranged in parallel configuration, if I had one cell here and one cell there, then I would be using the formula Vt equals V1 equals V2 equals V3. So that would be then my total voltage would not be 9, it would be 4.5. But because they're arranged in a series configuration, I have to use the series equation, even though I'm going to use the parallel equation to calculate my resistance in this circuit because my resistors are arranged in a parallel configuration. All right, what would the total resistance of the circuit be? Here's what I've got to use my 1 over equation. So I'm going to have 1 over RT equals 1 over 3 plus 1 over 1 plus 1 over 0.5. Okay, 1 over 3, 1 over 1, 1 over 0.5. I'm going to have to multiply these out to get a common denominator. So I'll go to 3. So that's going to be 3 over 3. That's going to be 6 over 3. So I'm going to have, essentially what I'm going to have is 1 over RT equals 10 over 3. But it's 1 over RT, so I got to flip that around. So RT now becomes 3 over 10, which equals to 0.3 ohms. That's my total resistance in this circuit. Compare that to the series circuit where I had 3 resistors in series. I had a total resistance on the series circuit on the last page, which is 4.5 ohms. I got the same amount of resistors now. They're in parallel configuration, and I've only got 0.3 ohms. You can see the huge advantage of running parallel circuits as far as total resistance is concerned. It really does reduce the total resistance. But that's basically the calculation that I just gave you. And here's all the calculations for it right there on the page. I just filled those out for you as well. All right, what's the current measured at position Z? Position Z. So now I've got my voltage, I've got my resistance. I should be able to calculate my current using Ohm's law formula. Pause me if you need to. Here comes the answer. In this case, I'm going to rearrange the equation. It's going to be current equals V over R. That's a rearrangement of the Ohm's law equation. Well, my voltage, as I mentioned, was 9.0 volts. Resistance is going to be 0.3 ohms, which is going to give me an answer of, it's going to be 30 amps. So my current on this sucker, but that current is only going to be applicable at Z. As I mentioned, because it's a parallel configuration now, that current is going to change depending on which part of the circuit we're on. Because when we get to here, there are multiple branches where all these total number of electrons are going to flow in different directions depending on how much resistance is in each part of the parallel circuit. For example, most of the electrons are going to flow this way because here's where the least amount of resistance is. The second most amount of electrons is going to flow this way because it has the second highest resistance, and the least amount of electrons is going to flow this way. So in theory, not Siri, it doesn't trigger there. This is going to have the lowest current. So I'm making a prediction right now. Y is going to have the lowest current. W will have the middle range current, and V will have the highest current. And in theory, if I took all 3 of these currents together, they should equal X, which also should in theory equal Z. Because here I have a total number of electrons that are flowing in one path. They're going to separate into 3 paths, and then they're going to come back together into one path. I'm not losing any electrons. I'm just dividing them. So in theory, these 3 numbers here are going to equal, they should equal 30 amps. As well, X should also be 30 amps because, again, I put all the electrons back together again. I put Humpty Dumpty back together again. All the electrons are flowing in that part of the circuit now. Let's see if that theory plays out. What's the current at position Y? Well, how do I calculate it? Pause me if you need to. I'm going to do this. Now that I know what I'm going to use for all of these now, is I'm going to use my voltage. Because my voltage doesn't change. And it's because it's a parallel circuit, my voltage is always going to be consistent. So I'm going to use my 3 ohms, because that's my resistors of resistance, and I'm going to use the voltage. So I'm going to calculate it as I equals VR, which is going to be 9 divided by 3. My current there is going to be 3 amps. I'm going to run all these numbers at the bottom just to see how they all plug together. In theory, we said that the total number of amps for the position Z is 30 amps. So in theory, I should have 3 numbers here that are going to add up to 30. Let's see if that actually works out. Next one, let's do W. W is going to be 9 divided by, in this case now, 1 ohm of resistance. That's going to give me 9 amps. Okay, so I got 3 plus 9. That's beautiful. And then one more, let's do position V. I'm going to take 9 divided by half an ohm. That's going to give me 18 amps. Well, look at that, folks. 3 plus 9 plus 18 equals what? 30. The math works. So again, at position X, we're going to have 30 amps. Z, we're going to have 30 amps. Y is going to be 3 amps. W is going to be 9. V is going to be 18. And all the way through this parallel configuration, the voltage always remains the same. There you go. Got it? Think you got it? Find out. Watch the video and see how much of this actually does make sense as I walk you through calculating resistance and voltage and current in parallel versus series circuits. Here's the homework. See what you got there, folks. This is, I like this stuff. It's kind of problem solving, not that difficult. The math isn't very difficult. It's just knowing how to use the equations. Let's do a few questions here. Let's do 34, 35, 36, 37 on pages 376 to pages 381, and questions 1 to 13 on page 384. That is your homework for tonight. Next day, we're going to finish up electricity and magnetic fields, first half of the unit. This is our last concept coming up. We're going to be starting to talk about our thing called transmitting electrical energy, and we're going to have some discussions about that, about power and efficiency. And yeah, what's the difference between energy and power? Even though they call them power bills, we're paying for energy. So they should be called power bills, or they should be called energy bills. I'm going to have that discussion with you next day. Thanks for tuning in, and until then, have yourself a good one.